sketch the base graph of y equals tangent of x, talk about the amplitude, domain, range, and period of tangent of x, and then determine any asymptotes and x-intercepts of the graph. Okay, so when we think of the tangent graph, what we want to think of, it's again related to our unit circle. If this is our unit circle and this is representing our point on the unit circle x comma y, okay, the tangent is, we're actually talking about how this tangent line, we call it a tangent line because it touches the unit circle at one distinct point, how this tangent line actually relates to the unit circle. So when we think about rotating around this unit circle, what we end up getting is this terminal arm. And if we extend that terminal arm, then that is giving us, it's actually crossing this tangent line at a certain point. And so when we talk about this, what the relationship is, we talk about the relationship of the slope of this terminal arm in relationship to the tangent. And so if we were to talk about the slope of this terminal arm in relationship to the tangent, technically the relationship of the slope of this terminal arm is going to be equivalent to this because of our similar triangles. So how do we find the slope of a line? Well, we think of slope of a line as being rise over run. In this case, our rise is our y value and our run is our x value. So the slope of this terminal arm in relationship to this tangent would always be y over x. And in terms of our unit circle, if this point is on the unit circle, our y value relates to our sine function and our x value relates to our cosine function. So that's where the tangent ratio comes from as well, is talking about the relationship of this slope to this tangent line. And so if we were to continue to rotate around this unit circle, right, no matter where I drew this line, it's eventually going to cross this tangent line at some point, which is going to have the same slope as this point on my unit circle. And then even as I start to rotate here, right, my terminal arm is here, but as I extend that terminal arm, the slope of this expression is going to be the same as this triangle here, which is going to be, in this case, as I rotate over here, here, and here, this slope is now going to be negative. So that's why our tangent value eventually becomes negative. Okay. Another way you can think of the tangent ratio is the length of the line segment tangent has to the unit circle at the point 1, 0 from the x-axis to the terminal arm. So another way you can think of this is, well, what distance does this have in relationship to this tangent point? Okay, and that distance will always be the equivalent to the tangent ratio. And the reason for that is because this point is never changing, right? Our tangent ratio, we know, is always opposite over adjacent. And in this case, the opposite will always represent our y value of this point, where however long that y value is. So technically this, another way to think of it is the tangent ratio is actually the distance between Q and A on this tangent line, because our adjacent value, which is x, our x value, because we're on the unit circle, this x coordinate value is always going to be 1. So technically our tangent ratio really represents this distance, and don't think of y as our sine ratio, you have to think of y as the distance between A and Q. Okay, so that's another way you can think of what this tangent ratio is doing, is it's actually giving us the distance between our A and Q values. Okay. All right, so now we're going to move on and actually graph the base function of our tangent graph, which actually looks quite a bit different than our cos and sine graphs. Okay, so similarly, what we did with our sine and cosine graphs is we're going to go through our unit circle and we're going to plot each of these points to get a good idea of what our graph is going to look like. So at 0 degrees, our tangent ratio at 0 is 0. At 30 degrees, it's 1 over root 3. It's approximately 0.58. So if I were to start to plot these points, 0 at 30 degrees is 0.58, so just past 0.5. At 60 degrees, we have root 3, which is 1.73. At 90 degrees, we're taking remember we're always taking our y value and dividing by x, so anything divided by 0 is undefined. So what happens at that undefined point is we actually get what we call a vertical asymptote. So at 90 degrees, because the graph is undefined, we get this vertical asymptote occurring. Okay, and then again at 120, our value is a negative root 3, which is negative 1.73. So our value now is approximately here. 150 is negative 1 over root 3, which is 0.58. At 180 degrees, we get a value of 0. 210, we get a value of positive 1 over root 3. 240, we get positive root 3. At 270, again, we get this undefined value. So again, at 270 degrees, we get what we call a vertical asymptote showing up. So our graph is going to approach these lines, but actually never cross them. Negative root 3. Negative 1 over root 3. And 360 is 0. So what we start to see is this pattern happening. Okay, if again we worked in the negative rotation, we get this.
I am your new forklift.
We get the same values but working backwards. This would be undefined. Okay, so if I start to plot these points going the other direction, at negative 90 we have this asymptote occurring again. Negative 180 should be 0. Negative root 3. This should be 0 again, or undefined, sorry. We get this vertical asymptote occurring at negative 270. And then finally, just finishing this off, it'll be 0. Okay, so if you can start to kind of see a pattern, and it's almost easier to see the pattern in between a set of asymptotes. So remember, our graph wants to approach these asymptotes, but will actually never cross them. So what's going to happen is our graph is going to come up close to these asymptotes, go through the points I've created, and it's almost creating this S type of shape, and it's going to repeat that S type of shape through every set of asymptotes. Okay, so there is what the tangent graph looks like. So as you can see, that the base tangent graph is definitely takes on a very different shape than our cosine and sine graph. Okay, and same with the characteristics. The characteristics are going to be a little bit different as well. Okay, so the period of our tangent graph is no longer 2 pi like sine and cosine. It's going to be pi, so this is repeating itself over 180 degrees. There is no amplitude value, so we don't talk about an a value. You can have an a value attached to your tangent function, but we actually don't call it the amplitude. Okay, you should never have a max or minimum point with a tangent graph because the graph continues off in both directions. We do, however, have asymptotes, which is a little bit new to us. And so where are asymptotes occurring? So our asymptotes are occurring at 90 degrees plus every 180 degrees after that, or in terms of radians would be pi over 2 plus n pi's, where n would have to belong to the integers. Similarly, our domain, when we talk about domain is going to represent all real numbers, except for our domain cannot occur, it's broken up, at these asymptote marks. So when we talk about the domain of a tangent function, we have to take away or not include our asymptote points. So we're going to say x belongs to real numbers where x cannot equal pi over 2 plus n pi every n pi, where n belongs to the integers. Our x-intercepts are occurring at 0, 180, 360, and so on. So that would represent every n pi, or if this was in terms of degrees, would be every 180 n, where n belongs to the integers. And then the y-intercept occurs at 0. Okay. Tangent functions, we really do not transform very much. Okay, you might be asked a simple, like if you had an a value attached to the tangent function, you might be asked like, what is the stretch factor of that? Or you might have something very similar, very simple to like, this has been moved so many units to the right. So transformations are going to affect a tangent graph like cosine and sine functions, but we really don't, you won't be expected to sketch a transform graph. You might just be able to have to talk about the transformations from a function. Okay, so you don't have to sketch a transform graph of a tangent graph. You just have to have a good idea of what that base function looks like and recognize that it has asymptotes, be able to identify where those asymptotes are going to occur, and as well as your x-intercepts. Okay. All right, so moving on, how do we modeling a tangent problem? Okay, so it says a small plane is flying at a constant altitude of 6,000 meters directly towards an observer. So this is 6,000. So here's the observer. The plane is 6,000 meters high, right? That's altitude. Assume that the ground is flat in the region close to the observer. Determine the relation between the horizontal distance in meters from the observer to the plane and the angle in degrees formed from the vertical to the plane. So we want to talk about the relationship of this horizontal distance the relationship between the horizontal distance, the vertical, and the angle that it's creating with the observer. So obviously, as the plane gets farther away, this way, this angle is going to get smaller. It's going to decrease. As the plane gets closer to the observer, this angle is going to gradually decrease until at some point, right, the plane is actually going to cross over the observer and continue in this direction. So when we talk about this relationships, well, if I talk about just simple opposite, adjacent, hypotenuse, if this is my angle, this would be the opposite of that angle. This would be my adjacent. So the relationship would be d over 6,000.